Hello all, I am Akshay working with Professor Manoj on this research with the Supergen Bioenergy Hub. This project focuses on transforming biogenic waste into clean hydrogen using the Hydrogen-BECCUS concept. Today we face three major challenges: rising waste, increasing carbon emissions, and a growing demand for clean fuels, especially hydrogen. Tackling these challenges together is critical for a cleaner and more sustainable energy future. Our research plan is to develop an innovative Hydrogen-BECCUS concept integrating robust thermochemical processes. By using pyrolysis-assisted gasification and integrating it with other subsystems for hydrogen enrichment, various feedstocks and blends such as municipal solid waste, biomass, and agricultural waste are being studied. The aim is to identify the optimal parameters and blending ratios for maximizing hydrogen production while capturing carbon. To achieve this, we use high-level mathematical and computational software packages for advanced modeling, including computational fluid dynamics, along with overall environmental assessment using the latest inventories and standards. First, we performed system-level validation to build confidence in the developed subsystems of gasification, calcium looping, and pressure swing adsorption. System-level validation studies were conducted using benchmark cases from previous literature. More than 30 studies were analyzed to evaluate the robustness of the model under different operating conditions and feedstocks. Our first integrated model is shown here. The simplified schematic demonstrates how the hydrogen-optimized gasifier sends captured carbon dioxide for regeneration and isolation, while the remaining gases are sent to the PSA unit to obtain 99.99% purity hydrogen. Different feedstock blends involving plastic waste, municipal solid waste, and wood biomass were analyzed to identify the optimum blend for hydrogen production and carbon capture. After rigorous sensitivity analysis of the system, the initial results are highly promising. The system achieved up to 93% hydrogen production while capturing nearly 90% of carbon dioxide in situ. To better understand the reactor behavior, computational fluid dynamics modeling was carried out to study particle distribution and reactive flow inside a fluidized bed gasifier. This helped improve process understanding and optimize reactor performance. Initial life cycle assessment results showed that we are able to achieve negative emissions with minimal heat recovery while using cradle-to-gate boundary conditions. When discussing scale-up, it is necessary to understand whether the project will be energy efficient. The three developed scenarios showed promising results, with maximum hydrogen production and minimum energy loss, even without considering energy recovery. Techno-economic studies were further performed to evaluate hydrogen production cost and energy efficiency under different recovery scenarios. The best-case levelized cost of hydrogen was found to be 7.87, while the levelized cost of carbon capture was 1.42. Two of the scenarios were highly profitable over the complete project lifetime, while the base case was unable to reach the minimum threshold required for returns. Experimental investigations further supported the modeling results through feedstock analysis and gasification studies. The experimental setup for steam gasification was similar to the modeling approach, but it was carried out in two stages. First at 650 degrees Celsius for sorption, followed by regeneration at 1100 degrees Celsius. Initial investigations were conducted across pyrolysis, air gasification, and steam gasification. The results from steam gasification and pyrolysis showed higher carbon capture potential and hydrogen production compared to air gasification. Future plans involve developing deep kinetic integrated modeling with optimized feedstock blends, along with simultaneous life cycle and techno-economic assessment for optimization and de-risking scale-up. To take the project further, we are also collaborating on potential sustainable aviation fuel routes using biosyngas and byproducts from gasification. Overall, this research demonstrates a promising pathway for producing clean hydrogen from waste while contributing towards net negative emissions. Please get in touch for any queries or further information. Thank you.